Alrighty, so in this video we will be looking at another technique for analyzing circuits that tends to pop up every once in a while, and it's called DeltaY transformations, or also sometimes, so delta Y, sometimes you may also see it as T pi transformations. Okay, it's just, and you'll see as we get into it, delta and T connections of resistors are equivalent. It's just, are you drawing it to look like a delta? Delta and pi are equivalent, and Y and T are equivalent. It just, one looks different than the other when you draw it out, but we'll see that they actually tend to be the same thing. But usually when we get into this type of technique, it's known as delta Y transformation. Sometimes they'll spell out Y, so you'll see delta Y, something like that. And basically it goes like this. Say you have a circuit, and in this circuit you have resistors connected in such a way that it doesn't seem necessarily to be just strictly series or parallel, but kind of some weird connection. For instance, maybe you'll have a set of resistors, something like this. So maybe that's your point. You come in, or let me do it like this actually. Okay, we'll have one resistor like this. Oops. One resistor like this, one resistor like this. So you may have some combination of resistors. I'll call this R1, this will be R2, and this will be R3. Okay, and these terminals over here, maybe they connect to a different part of the circuit. So I'm just kind of focusing on one little section of the circuit with the resistors like this. This, of course, is called a Y connection. Okay, and obvious, it looks like a Y. You can also see it a little bit differently. It's exactly the same connections, but it looks like this. Where this is R1, R2, and R3. Okay, you can see these two are the same. It's just one, they're drawn with diagonal resistors, R1 and R2, whereas they're just drawn straight in the other one. This is called a T connection. Okay, and, is R1 and R2, they're not connected in series because R3 is sitting there in between them. But they're also not in parallel because they don't share two nodes in common. So it's some kind of a weird thing going on, and we may need to figure out how do we deal with something like this. Well, it's possible to convert your Y connection into what's called a delta connection, or your T into what's called a pi connection. So let's look at what the delta looks like. The delta looks like this. Okay, I'll call this RC, RB, and RA, and you'll see why I'm naming them like this a little bit later. This we'll call the delta connection because it looks like a triangle, an upside down triangle. That's a delta in Greek. And of course we could also draw it like this. Instead of having them at diagonals, they're just connected like that. This is a pi connection. This is RC, RA, and RB. Okay, so we have a Y connection on the left and a delta connection on the left here. And what my claim is that If you start with a connection like the Y, we can convert this set of 3 resistors into a different set of 3 resistors connected in the delta formation. So 1, 2, and 3 are not going to be the same as A, B, and C. They're going to be different 3 resistors. But the way this connection reacts to the rest of the circuit is equivalent. So I could either use the Y and try to solve my circuit like that, or if I get stuck, I can convert it into a delta connection, and maybe that helps me further my analysis later on. And of course, the same can be said for the T and the pi. I'm going to use, right now, delta and Y just because that's what I'm more comfortable saying most of the time. That's what it's known as. But everything I say about delta and Y is the same for pi and T. All right, so how do we convert between these two types of connection? So here's the theory. It goes like this. Say I have a delta connection. It looks like this. And I'll call this C, A, and B. And I want to convert it into a Y connection. And I'll call this 1, 2, and 3. The claim is that there is a way to convert the first connection, the delta, into the Y for some set of resistors, A, B, and C, and 1, 2, and 3, such that they're equivalent. And it goes like this, and this is going to be the reason I named these things this way. Again, A, B, and C are going to be different resistors than 1, 2, and 3. That's why I gave them different names. But more than that, I've labeled them in a very specific order. Okay? Notice my 1 resistor here is kind of this top left resistor, and my A is like the bottom right resistor of the delta. The 2 is the top right, the B is the bottom left, almost like they're opposites of each other. And then the 3 in the bottom middle goes with the C, which is the top middle. And one way to visualize this is to take, let's say, my Y connection and put in my delta connection on top of it, overlaid. Okay, so this is C, A, B, and this is 1, 2, and 3. So notice 1 is across from A, opposite to A, 2 is across from B, and C is across from 3. That's how I've labeled it, and the reason, usually it doesn't matter how you label it, it's just a name, who cares what you call it. The reason I'm labeling it this way is because it'll make the equations we're about to use to figure out what must be A, B, and C, or 1, 2, and 3, more easy to understand. In other words, if you forget the equations, because there's got to be a lot of different terms in it, you could just look at the picture and tell, okay, should it be R1 times R2, or is it R1 times R3? What's it going to be? And it's this opposite relationship. A is kind of connected with, not connected to, but kind of connected with resistor 1. B is kind of with resistor 2, and C is with resistor 3. And just kind of like, well, they're opposite of each other. Like when you have a right triangle, we say theta is here, the side opposite to the angle is the opposite side. Same thing here. All right, so how do we do this? How do we actually find out given we have the delta connection and we have A, B, and C already, so we're given a circuit, here are the three resistors, I want you to tell me what should the Y connection of three other resistors be that give me the same result. And this is the equation to go from delta to Y. So delta to Y. So first, remember, we know A, B, and C. We know these numbers. I'm trying to figure out what are 1, 2, and 3. So R1, the value of resistor 1 in the Y connection, is going to be RB times RC over the sum of all three, RA plus RB plus RC. Okay? Now the way I remember this is, again, I'm associating resistor 1 with resistor A. They're opposite to each other. They're associated with each other. So I remember the equation is the product of the other two resistors, the one not associated with 1, divided by the sum of all the resistors. So for R1, R1's associated with RA. I don't care about that one. I want the other two, B and C. And then I divide that by the sum, A plus B plus C. Likewise, for R2, same exact rule will apply. R2 is this top right resistor. It's associated with B. So I need the product of the other two resistors, not the B. So that's RA times RC divided by the sum, RA plus RB plus RC. And finally, R3, it's easy to see. 3 is associated with C, so that's the product of the other two, RA and RB, divided by the sum, A plus B plus C. Okay, so you're going from a delta connection to a Y connection. You're trying to find out what are the three resistors for the Y connection. If you want resistor 1, that's the resistor which is opposite to resistor A when you draw it. You take the product of the other two resistors, not A, so it's B and C, divided by the sum. For resistor 2, the one opposite to the resistor B, you take A and C, divided by the sum. And then finally, for resistor 3, it's A and B, divided by the sum. So now let's say we want to go the other way. Say we're given a circuit which has a Y connection in it already, and I'm trying to figure out how to convert it to the delta connection. So I want to go from Y to delta. How do I do this? Well, in this case, I'm going to know resistors 1, 2, and 3, and I'm trying to come up with an equation that has A, B, and C in it. Now, the first thing you could try to do, if you want, is take the three equations for delta to Y and solve them for A, B, and C. So you have three equations with three unknowns, and you try to algebraically manipulate everything to get them. That's perfectly fine. It's a pain in the butt. It's not difficult. It's just you got to be patient and be organized and follow the algebra. The result of the algebra goes like this. Say I want RA. Okay. Well, the rule to go from Y to delta says in the numerator, you're going to take the product of all three of these resistors pairwise. So all the different combinations of multiplying two resistors together. Okay. So I have resistor 1 times resistor 2. That's one pair. Plus resistor 1 with resistor 3. That's another pair. And then the only one I haven't done is resistor 2 and resistor 3 multiplied together. Right? So I have three resistors. I'm going to multiply pairs, and I'm going to add all the possible pairs together. So the pairs are 1 and 2, 1 and 3, and 2 and 3. Then I'm going to divide this by something. And similar in the delta to Y thing, remember 1 is associated with A, 2 is associated with B, 3 is associated with C. For the Y to delta, If we want RA, then I divide by the resistor associated with RA. In this case, that's R1. Okay. For RB, what do? Exactly the same thought process. We're going to have in the numerator the sum of all the pairs. So R1, R2, plus R1, R3, plus R2, R3, divided by something. What do I divide by? The resistor associated with B, the one I'm looking for, which is R2. And then finally, RC is the last one. It's the same product of pairs, R1, R2, sum of the products, R1, R3, and then R2, R3, all divided by R3 in this case. So A goes with 1, B goes with 2, C goes with 3. That's, again, it makes it a little easier to remember this if you associate the labeling here the way I've done it. If not, if you just label them randomly, then instead you have to try to remember like the actual physical location of these resistors and how they relate to each other. The way I've labeled them, so A is across from where 1 would be, B is across from where 2 would be, and C is across from where 3 would be. However you do that, then these equations kind of give you themselves. For delta Y, you take the product of the resistors not associated with the resistor you're talking about. So for instance, for R2, R2 is associated with RB. So I want the product of the two resistors not RB, so RA times RC, and then divide by the sum of all the resistors. Different going from Y to delta. For Y to delta, the numerator is the sum of all the different pairs of resistors you can have. In this case, there's 3 pairs. And you divide that by the resistor associated with the one you're trying to find. So if you want RB, you divide it by R2. Okay? Again, if things are labeled differently, then you just have to manipulate your labels in these equations to match how you label your resistors. But I highly advise you label them kind of the way I have, just to make your life a little bit easier. Now let's try an example. Okay, let's take a clear example of how to actually do this. Say I have this set of resistors, 1, 2, and 3, like this. This will be 30, this will be 20, and this will be 50. And I want to convert it to a delta. It looks like this. Okay. So what I'd like to know is, let's say I call this guy RA, I'll call this guy RB, and I'll call this guy RC. Let's say that's how I label them here. How do I label the Y, or the T in this case? Remember, T and Y connections are the same, they just look slightly different. Rather than being at diagonals, they're straight across. How would I label my T connection to match my delta connection to make my equations easier? Well, if I have RA here as the top in the middle, opposite to that would be the 50, the bottom middle. So I'll call this R1. RB is over here, the bottom right, so opposite to that is going to be the top left resistor, the 30, so that's going to be R2. And then RC, the bottom left, is going to be associated with R3, which has to be the top right, opposite to where that resistor is, so this is R3. Okay, so given the labeling on the right, I have labeled my T connection on the left to kind of match the way my equations go. Now the question is, find RA, RB, and RC. Okay, well, given I'm looking for the delta. So it's like I'm going from Y to delta or from T to delta. Going from T to delta, I know the equation RA is going to be the pairs R1, R2 plus R1, R3 plus R2, R3, all divided by the one associated with RA, that's R1. So plugging numbers into this, R1 times R2, that's 50 times 30, plus R1 times R3, that's 50 times 20, plus R2 times R3, that's 30 times 20. All of that's divided by R1, which is 50. Now notice how important it is to label these things correctly. If I can't just willy-nilly call one of these resistors R1, I have to make sure that if I'm going to go by the way I've written out my equations, R1 is that resistor which is opposite to RA in location, and 2 with B and 3 with C. Okay. So plugging numbers in, what do we get? This is 1500 plus 1000 plus 600 all over 50. Okay, so 1500 plus 1000, that's 2500 plus 600, that is 3100. 3100 over 50 is the same as 310 over 5. Okay. 5 goes into 31 6 times with 2 left over, so it's 62. So RA would have to be 62. Okay. Now I need RB. Okay, well RB, that's just going to be the pairs. Well, I've already done the pairs. I'll write it out. R1, R2 plus R1, R3 plus R2, R3. And now, if I'm looking for B, I divide it by R2. Well, we already know the numerator is the same number as the numerator for the first one, right? It's still the sum of the pairs, so that's still 3100. But this time, instead of dividing by 50, I'm dividing by R2, which is 30. Okay, so that's 310 over 3, which is 1, and then a 3.333. So 13.333, I believe. I'm sorry, that's 103. What am I doing? 13. 103.33. I forgot a 0 there. All right, so there's RB done. I've got RA is 62, RB is 103, so RC, the last one, again, I've got the pairs, R1, R2, plus R1, R3, plus R2, R3, divided by, if I want C, this is divided by R3. So the numerator is the same, 3100. R3 is 20, so this is 310 over 2, which is 2 goes into 3 once. 11 is 5, and 2, 152, 155 actually, 155. And there we go. So if I make RA 62, RB 103.333, and RC 155, then this delta connection of those three resistors act equivalently in a circuit as R1, R2, and 3 resistors connected as a Y. All right, well, let's try this in an actual circuit. Let's see how this works with a real circuit and see why this might be helpful. Okay, so for now, this is just an interesting little trick, but why would we want to do this? So let's take this example here. We have this. say we have this circuit here. I'll call this, I don't know, 10, 3, 2, 2. Let's do 3, 4, 5. Okay. So let's say what I'd like to do is find the total resistance. Maybe I'd like to find the total current which will flow through this circuit. So the first thing I want to do is find the total resistance of this circuit. Well, we could try the different techniques we know. Maybe we do loop analysis or nodal analysis or something like that. But notice what we have right here. Right here, we have one of those T connections, and a T is the same as a Y. So maybe what I'd like to do is take this connection of resistors three, 4, 5, and convert it into a delta that looks like this. Okay, so how do we want to do this? Let's call this R1, this will be R2, and this will be R3. Just completely arbitrary. I've chosen those arbitrarily. Now, because I chose those the way I have, then what I have to do is I say, okay, the R3 in this, bottom middle, or basically the straight to the left, that will be the same as this guy over here, RC. Okay? The top, R1, is going to be associated with the bottom over here, RA, and the bottom R2 is associated with the top over here, RB. Okay? It's always like the opposite. R3 is on the left, RC is on the right. RA is on the bottom, R1 is on the top, and so on. So what I'd like to do is figure out what should RA, B, and C be such that I could replace that thing I've circled in gray with this new delta connection instead. Okay, well, let's try it. We get RA is going to be, just like before, we have the product or the sum of the products of the pairs. So 4 times 5 plus 4 times 3 plus 3 times 5. That's all the pairs, 1 and 2, 1 and 3, and then 2 and 3, divided by, if I want RA, I divide it by R1, which is 4. Okay, so this is 20 plus 12 plus 15 divided by 4. So 20 and 12 is 32, plus 15 is 47, so this is 47 over 4. And for now, I'll just leave it like that. Okay, I could put the decimal 11.7 or whatever it is, but I'll leave it like this for now. All right, RB is going to be the same top, 47, over now the denominator is going to be R2, which is 5. Okay, and I'll leave it as that, 47 over 5 for him. And then RC is going to be the 47 divided by R3, and R3 is 3. All right, so now what do I have? Let me redraw this on the next page just so we have some room. So I have this, bear with me here, this, this. Okay, so far that's the 10, 3, 2, 2. And now, instead of what's in gray there, that T, I'm going to replace it with this delta I wrote, right? So the delta looks like this. This thing, and this thing. Right? Now I just fill in the lines here. These were connected before. And now what do I have for these pieces? RC is 47 over 3. So this is 47 over 3. I've got RB, the top, is 47 over 5. 47 over 5 there. And then 47 over 4 for that guy, RA. Okay. Now, you say, well, this certainly doesn't look any easier than this first one I had. It looks kind of miserable, actually. But notice something. Notice right here, these resistors, if you look at them, this is just one big node here, and this is one node here. So those two resistors are actually in parallel. And of course, the same is true for these resistors down here. These two resistors are also in parallel. So if I take the gray ones, I have 1 over R parallel is 1 over 2 plus 1 over 47 over 5, which is 1 over 2 plus 5 over 47. I want to add these together. Common denominator, let's see, what's the common denominator here? So this is 47 over 94 plus 5 times 2 is 10 over 94. So that's 57 over 94, or our parallel is 94 over 57. Okay? Miserable number, but that's what it is. Whatever this number is, you could use the decimal if you want. I'll just leave it as a fraction. And then, of course, I'll do the same for the yellow piece. The yellow piece, 1 over R parallel, is 1 over 2 plus 1 over 47 over 4, which is 1 over 2 plus 4 over 47. Again, common denominator. Tells me this is 47 over 94 plus 8 over 94, which is 55 over 94. So RP is 94 over 55. All right, so I've now combined those resistors together in parallel. And so now what do I have? This becomes, this is still the same, this is still the same, these things haven't changed. And now this 2 and 47 over 5 parallel thing becomes a single resistor. There he is. And his resistance is 94 over 57. And then the yellow ones, the 2 and the 47 over 4, becomes its own resistor, who's 94 over 55. And then what do we have left? Just this piece sticking out at the end, which was the 47 over 3 we haven't messed with yet. And now we see we're exactly where we need to be. Now there's nothing weird, no strange connections. I've got the 3, this branch, and this branch all in parallel with each other. So I could combine the 2 in the middle branch as a series to get a single resistor. Then I'll have 3 resistors in parallel. I just combine them in parallel and I have my total resistance. Okay? The rest of this is just what we've been doing since the beginning of the semester. The unique thing is the beginning here. We start with this circuit. Now, under normal circumstances, you could try whatever method you want to try to figure this stuff out. Use loop analysis, use whatever you want. However, if we're going to try to practice this technique, which is helpful, then we say, okay, let's look for anything in our circuit that looks like a delta, a y, a t, or a pi. And indeed, I see a t. In fact, I see 2 t's. I could have done the 2, and the 3, this left side over here. Or what I did was the 3, the 4, and the 5. I said, okay, that's a t connection. So I can convert that into a delta connection. Now, it might be that this is not helpful. I don't know if it's going to be helpful yet, especially if I don't have enough experience with working circuits and stuff like that. This is just, I'm trying it. I'm going to see where it leads. Hopefully it makes things simpler for me. If it doesn't, if when I do this, things get even more complicated and I have no idea what to do next, then I just abandon this technique and try something else. But for this, obviously, I've set up this example so that it actually works. So I say, okay, I see a T connection. Let's try converting the T into a delta. How do I do it? I take the T I'm talking about, and then I label those resistors 1, 2, and 3. I can choose how I label them 1, 2, and 3. It doesn't matter. In this case, I chose the 4 to be 1, the 5 to be 2, and the 3 to be 3. But I could have changed that. However, once you've set those labels, the delta labels come from those. So, because I made the 4, this top resistor up here, I made that the 1, then in my delta, the guy that's on the bottom opposite in location to where that resistor is, that's the one I'm going to call A. This 3 over here to the left, he's opposite to the C, which is on the right. And then, of course, the bottom resistor here, 2, that's opposite to the top resistor, so I call him B. 1 goes with A, 2 goes with B, 3 goes with C. Once I've labeled them like this, then the equations as I've written hold perfectly fine. The equation says if I'm looking for RA, first thing I do in the numerator is I'm going to add up 3 terms, and those 3 terms are just the pairwise products. So I've got 3 different resistors. I'm going to pair them up in every combination. So I'm going to have 3 terms. And it's going to be R1 with R2, R1 with R3, and R2 with R3. And then I add those things together and I have some numerator. I'm going to divide that number by something. The thing I divide by is that resistor associated with the one I care about. So if I care about RA, the resistor associated with A is 1. That's why I labeled it this way. And then likewise for B and C. If I want B, it's the same numerator as A, but now instead of dividing by R1, I'm going to divide by R2. And C, I'm going to divide by R3. You do that and you're going to get 3 new resistors. These numbers are different than the starting numbers. Now, I redraw my circuit so that, and let me go ahead and take these circles away just so it's a little bit easier to see. I redraw my circuit where instead of the T, as I had before with the 3, 4, 5, I just draw in the delta instead. Once I do that, I now have some new circuit, and it's this circuit I have to work on. So I start looking at it and see, what can I do? The only natural thing I can see in trying to do this is looking for parallel stuff and looking for series stuff. Notice the 2 and the 2, these 2s, are not in series because you have this thing in the middle messing with them. The 3 is not in parallel or series with the 2s yet. It will be eventually, but we have to simplify the right side before we can hit it with the left side. And in this 47/3 over here on the right side, he's kind of stuck as well because he's neither in series or parallel with any one of these resistors. However, when we notice that these 2 resistors here are parallel with each other, and these 2 resistors are parallel with each other, then I can combine them in parallel, just like I've done in the past, and redraw my circuit where those 2 resistors in parallel combine to be 1 resistor, this guy right here, and this guy right here for the other set. And now I look at this circuit and I say, things are nice and easy. This is like first week of circuits. I've got some set of resistors. They're all in series or parallel or both. So I little by little simplify it down till I get the total resistance. Okay? That's what delta-Y conversion is all about, or delta-Y transformation. So I hope this makes sense. Of course, look online to find more of the examples, practice problems and solutions and stuff to get more practice about it. But it's all about look in your circuit. Do you see anything that looks like a T or a Y or a triangle delta or a pi? And if so, try, especially if we're in this chapter, try taking it and transforming it into its opposite. If you see a T, transfer it into a delta. If you see a delta, transfer it into a Y or a T, whatever. And then see where that leads you. Hopefully it helps. If not, then go try some other technique. You know, if this is a final exam where it's all cumulative, you don't know if you have to use delta Y or something else. Anyway, hope this is helpful. If you have any questions, let me know, and I'll see you next time.